always asking these questions, aren't we? Things like, did this new policy actually cause that shift we saw? Or maybe, did that health program we rolled out really have the effect we hoped for? Just a fundamental human thing, wanting to know why. And that's exactly what causal inference is about. It's about getting rigorous answers to those why questions. So today we're doing a deep dive into one of the cornerstone methods for this, difference in differences, usually just called D. But importantly, we're not stopping there. We're also looking at how cutting-edge machine learning, specifically something called Debiased Machine Learning, or DML, is, well, really turbocharging this classic approach.
That's exactly right. Our mission today, drawing from that applied causal inference material, is to really unpack DD for you, show how it works, what its key assumptions are, and then, critically, show how DML adds this layer of robustness and flexibility, especially when you're dealing with, messy, complex, real-world data. It's all about getting to answers you can trust and doing it efficiently, even when there's a ton of information flying around.
Okay, let's jump right in then. What exactly is difference in differences at its heart? And why does it feel, well, so intuitive when we're trying to pin down cause and effect?
Yeah, it is quite intuitive. Basically, DD needs two main ingredients, two groups and two time periods. You've got your treatment group, the ones who get the policy or the intervention, whatever it is,
Okay.
and then your control group, the ones who don't.
Right.
And you look at them before the intervention, that's the pre-treatment period, and after the post-treatment period. The standard DD analysis then just compares the change in the outcome for the treatment group to the change in the outcome for the control group over that same time.
So it's literally the difference between the differences.
Exactly. That difference of differences is how you try to isolate the actual causal effect of the treatment, stripping away any general trends that might be happening anyway.
Okay, now here's where I always get a bit stuck. The core assumption, this parallel trends idea, what does that actually mean, and why is it so absolutely crucial?
It's fundamental, really. The parallel trends assumption says that if the treatment had never happened, the treatment group's outcome would have changed in exactly the same way as the control group's outcome did.
So they would have moved in parallel.
Precisely. Think of those parallel worlds the source material talks about. You're assuming that the control group's trend shows you what would have happened to the treatment group without the treatment. It's what allows us to sort of impute that unobservable counterfactual what the treated group would have looked like. We use the control group's change as a proxy.
Okay, that makes sense. Like using the control group as a crystal ball for the treated group's what-if path.
Kind of, yeah. And there's another related assumption, too, no anticipation.
No anticipation.
Yeah. It basically means people in the treatment group didn't change their behavior before the treatment actually started just because they knew it was coming. That could obviously mess things up.
Right, they could definitely contaminate the before picture.
Exactly. And one more subtle point on parallel trends. It depends on how you measure your outcome.
What do you mean?
Well, just because trends might be parallel for, say, the level of wages, doesn't automatically mean they're parallel for the log of wages, which represents percentage changes.
Okay. So the specific way you define and measure your outcome variable really matters for whether this core assumption holds.
It really does. It's something you have to think carefully about.
All right, so assuming we have our groups, our time periods, and we feel okay about parallel trends, how do we actually calculate the effect, this average treatment effect on the treated, the AT? What's the math?
It's actually pretty straightforward. You calculate the average outcome change in the treatment group, post minus pre.
Okay.
Then you calculate the average outcome change in the control group, post minus pre.
Got it.
And you just subtract the second change from the first change. That difference is your AT estimate. It tells you the average effect specifically on those who receive the treatment.
And you mentioned it can also be done with regression.
Yeah, exactly. A simple linear regression with dummy variables for being in the treatment group, being in the post-treatment period, and an interaction term between those two. The coefficient on that interaction term numerically gives you the same ATT estimate. It's quite neat.
It's amazing how long this basic logic has been around. I saw the source mention John Snow and the cholera outbreaks in London.
Yeah, mid-19th century. He wasn't using regression, obviously, but his mapping and comparison of death rates between areas served by different water companies, it fundamentally used that DD logic, comparing the change in one area, getting dirty water, to the change in another, getting cleaner water. It's often cited as maybe the earliest quasi-experimental design.
That's fascinating. Let's jump to a more modern classic example, the Mariel boat lift study. That one comes up a lot.
It really does. It's a famous paper by David Card, a real prototypical application, as the source calls it. This is the context. May to September 1980, there's the sudden, largely unexpected arrival of Cuban immigrants in Miami, the Mariel boat lift. It increased Miami's labor force by something like 7%, pretty dramatically. Wow, okay.
And Card wanted to see, what impact did this sudden influx have on the low-skilled labor market in Miami? Specifically things like wages and unemployment for existing workers.
So the D-to-D setup here. Miami is obviously the treated city. What were the controls?
Card chose several other cities, Atlanta, Los Angeles, Houston, Tampa, St. Petersburg as the control group.
And the justification, the parallel trends argument there.
The argument was essentially that, absent the boat lift, Miami's labor market trends, particularly for low-skilled workers, would likely have tracked similarly to those other cities. They were chosen based on having, reasonably similar economic characteristics before 1980. It's always about finding the most plausible comparison group.
Makes sense. So what did Card find using this standard D-to-D approach? Did the influx hurt local workers?
Well, the results were pretty surprising to many at the time. The DD estimate for the effect on the unemployment rate of low-skilled workers was actually slightly negative, negative 1.1 percentage points.
Negative. So unemployment went down slightly. The point estimate was negative, yeah. But the standard error was 1.5, so statistically...
Not significantly different from zero.
Exactly. As the source puts it, it does not provide strong evidence of a large impact of the Mariel immigration on unemployment. A very influential finding.
Okay, so that's the power of classic D&D. But, like we hinted earlier, what if things are more complex? What if those parallel trends aren't quite holding or only hold if you account for other factors?
Right. That's where the story gets more interesting and where machine learning starts to play a really crucial role. Often, the raw parallel trends assumption might feel a bit strong, but it might be much more plausible to assume trends are parallel after you control for certain observable characteristics.
Characteristics like?
Oh, things like demographics, industry mix, prior economic conditions, stuff that might differ between the treatment and control groups and also affect the outcome trend. Let's call these characteristics X. So the idea becomes conditional parallel trends. The trends are parallel conditional on X.
Okay, I follow. You're making the comparison more apples to apples by accounting for these other factors.
Precisely. And this is where Debiased Machine Learning, DML, really enters the picture. DML is designed specifically for situations like this. It lets you use flexible machine learning methods, think random forests, gradient boosting, neural nets, whatever works best, to model the complex relationships between those X variables and the outcome, and between X and the probability of being treated. These relationships are what the source calls high-dimensional nuisance objects. They're things you need to estimate and control for, but they aren't the main effect you care about.
Nuisance objects. I like that term. Things you need to get out of the way.
Yeah, basically. DML uses clever techniques like cross-fitting to estimate these nuisance parts flexibly, and then it combines them in a specific way to get an estimate of your causal effect in the AT that's less biased and statistically robust, even with many controls.
This raises a key question, though. If we have these important X variables, why not just, throw them into that simple DD regression we talked about earlier? Just add them as linear controls.
That's a really important point. You can do that, just add, say, a beta X term to the regression. But the problem is, doing that doesn't necessarily give you the 8 you're looking for under conditional parallel trends.
Yes, then why not?
Without getting too deep into the math, simply adding linear controls like that often estimates some weighted average of effects across different types of individuals, and it relies on pretty strong assumptions about linearity or how the treatment effect relates to X. It might not recover a meaningful causal parameter unless those strong assumptions hold.
Okay, so it might give you an answer, but maybe not the specific answer. The average treatment effect on the tree that you actually want.
Yeah.
Exactly. The DML approach, particularly the double machine learning estimator for DD, is specifically constructed to target the AT under the conditional parallel trends assumption. It uses the ML models for flexibility, but structures the final estimation step to isolate that specific parameter.
So it's more targeted, more robust to how those X variables actually influence things.
Precisely. And often it's not much harder to implement these days with available software packages.
Okay, this sounds powerful. Let's make it concrete again. You mentioned another example where DML was used for DD minimum wage effects.
Yes, a study looking at minimum wage increases and teen employment in the U.S., a perennially debated topic. They used county-level data annually from 2001 to 2007. The outcome was the log of teen employment in the county.
Log, so percentage changes.
Right, and the treatment was defined as a county having a state or local minimum wage higher than the federal minimum. They focused specifically on counties where the minimum wage went up relative to the federal level in 2004. So 2003 and earlier was pre-treatment, 2004 to 2007 was post-treatment.
And what were the X variables they used for that conditional parallel trends assumption?
They included the county's population in 2001, average pay in 2001, teen employment level in 2001, and also which U.S. Census region the county was in. Basic baseline characteristics.
Yeah.
And importantly, they didn't just estimate one overall effect, they looked at dynamic effects, the effect in 2004, 2005, 2006, and 2007 separately.
To see how it evolved over time.
Exactly.
And what ML methods did they actually use within the DML framework to handle those nuisance functions?
They really threw the kitchen sink at it, which is good practice to check robustness. They used standard linear models, but also lasso ridge.
The regularized regressions.
Yep. And then random forest, various types of decision trees, deep trees, shallow trees, cross-validated trees. And they even use what they called a best ensemble method, which basically picked the best prediction model for each nuisance part based on cross-validation performance.
Wow, okay. So a real range of techniques. What did they find? Did DML give different answers about the minimum wage impact?
The findings were quite interesting. First off, some of the most complex models, like the deep tree, actually didn't perform as well in terms of predicting the nuisance parts.
Really? So more complexity isn't always better?
Not necessarily. It highlights that you need to be careful with model selection, even within DML. But the methods that did predict well, like lasso, random forest, the best ensemble, the majority of those pointed towards the minimum wage increase, causing decreases in teen employment.
Okay, so it did find a negative effect. Was it large?
The effects were generally small right after the increase in 2004, but they tended to grow larger in the following years, 2005, 2006. The source notes this pattern is economically plausible. Firms might take some time to adjust their staffing levels.
That makes sense. Did using the controls, the DML approach, change the size of the estimated effect compared to a simple D without controls?
Yes, and this was a key finding. All the estimates that included the control variables via DML found effects that were smaller in size, less negative than the basic D estimate that didn't use controls.
So failing to control for those county characteristics might have led to overstating the negative impact of the minimum wage.
That's exactly what the results suggest in this case. It shows the practical value of using DML to account for those confounders.
Were the effects statistically significant?
For the preferred best ensemble method, the negative effect on teen employment was statistically significant at the 5% level in 2005 and 2006. So yes, evidence of an impact.
Okay, but back to that crucial assumption. Conditional parallel trends. How did they try to validate that in this study? Did they do one of those placebo tests?
They did exactly that. It's often called a pre-trends test. They ran the whole analysis again, but pretended the treatment happened in 2002, which was before the actual minimum wage increases they were studying.
And the logic is, if the assumption holds, you shouldn't find an effect in 2002.
Precisely. If you see a significant effect before the treatment even happened, it suggests your treatment and control groups were already on different trajectories, even after conditioning on X. That would cast doubt on the main results.
So what did the placebo test show?
The results were reassuring for their main findings. Across all the different ML methods they used, the estimated effect for the placebo year 2002 was consistently small, both in absolute terms and relative to the standard errors.
So no red flags there.
Basically, yeah. They concluded there was no strong evidence of a violation of the underlying identifying assumption. But it's important to add the usual caveat. Failing to find a violation doesn't prove the assumption is true, and you generally shouldn't make your final inference conditional solely on passing these tests, but it definitely adds credibility.
Okay, so stepping back then, what's the big picture takeaway for someone listening? We've covered DD's intuitive logic.
Right, comparing changes over time, using a control group to figure out the what-ifs, a really foundational tool.
And then we saw how Debiased Machine Learning comes in, not just as a fancy add-on, but as a way to make DD more robust, especially when the world is complicated.
Exactly. DML lets you handle lots of control variables flexibly, helps you avoid biases like potentially overstating effects, and ultimately gives you more confidence that you're estimating the true average treatment effect on the treated. It sharpens our ability to answer that why question.
So maybe a final thought to leave everyone with. We've seen how much hinges on these assumptions, particularly parallel trends, even with powerful tools like DML. How could thinking about these specific assumptions help you, the listener, when you encounter causal claims out in the wild? Whether it's news about a policy, a study you read for work, maybe ask yourself, what's the comparison group being used? What parallel world are they implicitly assuming? And what factors might need to be controlled for to make that comparison truly fair? It's about critically evaluating the what-if story being told.